In this video, we are going to study the other optimizations that may help you on the final project, which is optimizing your compiler as much as possible. So we've learned various optimizations such as dead code elimination or control flow graph manipulation, GBN and mem2res and register allocation. For this video, we will learn other kinds of optimizations. So first class optimization is basically simple ones. This people optimizations is literally meaning that they are simple optimizations based on some arithmetic or other kinds of properties of the program. So here's an example. The first example is showing a code snippet here. So this y equals x plus 1 and z equals y plus 2. And suppose that y is no longer used in the remaining of the code. So y is only used here, and it is the only place where y is used. If that is the case, we may want to optimize this program into here. First of all, just removing y equals blah blah, because y is no longer used, and replace y plus 2 with x plus 3 because effectively z is y plus 2 which equals to x plus 1 plus 2, and by some simplification using addition's associativity we will know that g should be x plus 3, and as a result we can simplify this instruction into z equals x plus 3. Effectively, we are reducing the number of instructions by 1 because the first instruction is just gone. It is no longer a valid operation. It is null, which can be easily optimized later. Okay, so by using a simple arithmetic rules, in this case addition's associativity, we can simplify the code a little bit. Similar thing happen for other arithmetic rules as well. So suppose that we want to exploit the fact that addition is commutative. That means a plus b is always equal to b plus a for arbitrary a and b. So let's look at this code. Z equals x plus y, and we are defining w equals y plus x. So these two expressions are different only in the order of the operands, x plus y, y plus x. They are actually the same in the value. The form is a little bit different. The order is a little bit different, but except for that, they are exactly the same instructions. So but in the GBN optimization we implemented in the previous homework, it doesn't figure out that these two instructions are actually the same. Because they are different in form. But here, we may be able to deduce that, because addition is commutative, z and w is actually the same. So we can just replace w equals blah blah with w equals z. Or we can just replace all the uses of w with z, because w is always equal to z. So this is again exploiting a simple arithmetic rule, which is addition's commutativity, in optimizing a small snippet of the code. So such a small optimizations based on a simple arithmetic rule are called people optimizations. But it is well known that these kind of people optimizations are very beneficial for performance. So these people optimizations are usually implemented in the instruction combining paths in the Elimination compiler, and it is dealing with a significant portion of optimizations in the compiler's pipeline. Okay, the reason is that we not only exploit these additions, associativity and commutativity, but hundreds and thousands of such rules. So there are many arithmetic properties we want to exploit in the optimization. And actually LLVM is exploiting hundreds and thousands of such a rule. that's the reason why people optimizations are really effective in optimizing the given code, especially for some scientific computations or some computation intensive code which have many arithmetic operations. There are other kinds of people optimizations on memory operations. So here we are having two identical load. So in the GBN implementation, we didn't try to optimize it because the loads are affected by the intervening writes to the memory. So suppose that there is some code inside X and Y, then we cannot be very sure about the relation between these values of X and Y. So that's the reason why GBN doesn't handle this, and GBN only focuses on the registers. It doesn't deal with memory locations at all. But for this particular array of instructions where L is loaded twice and it is in series without any intervention, then we are quite sure that X and Y should have the same value because we are loading from the same memory in series without intervening with other instructions. So that's the reason why we can replace Y with X because they have the same value. So effectively, the second instruction may be replaced with Y equals X. Or even further, all uses of Y can be replaced with X in the remaining of the code. Similarly, or conversely, we can eliminate stores as well. If we are storing some values to the same location in series without intervention of other code, then we are quite sure that the first store is no longer relevant. We are storing X to L and then immediately storing Y to L, and that's the reason why this X is no longer used because immediately Y is overwritten to the location. And as a result, we may be able to eliminate the store, the first store whose value is not visible to elsewhere. So such an optimization is called store elimination or store merge. So this kind of optimization can be done in your program. And this is actually quite easy to spot such series of operations. And I strongly recommend you to implement such optimizations if you want to do well on the final project. So the more you implement such optimizations, the more your program will perform. And there are other classes of optimizations which mainly focus on memory optimization. So in this slide, I introduced only two optimizations that is very simple. Simple memory optimizations, load elimination and store elimination. This is simple in that there's no code between these two instructions, and we are quite sure about what's going on in these instructions. But even though there are intervening code, and even if the intervening codes are unknown to the compiler, we may be able to still perform optimizations for these memory operations. So in this slide, we are going to deal with such memory optimizations and some advanced memory optimizations based on what is called alias analysis. So in order to perform alias analysis, we need to make sure that the intervening code between two memory operations are irrelevant to the location of our focus. So in order to do so, we need to perform alias analysis, which checks whether two memory locations are pointing to the same location or not. So suppose that if this P and Q are pointers and they may point to the same location, then maybe assigning to Q or storing to Q may interfere with the value stored in P. If that is the case, we don't want to perform optimizations because it may break the correctness. However, on the other hand, if we are quite sure that P and Q are pointers and they point to two different locations, then we may be able to perform optimizations on P even though there is an intervening right to Q. So using this alias analysis, we may perform the advanced memory optimizations such as load store elimination, store forwarding, etc., etc. So here's an example. Load elimination. We already talked about this. If you have two consecutive loads, then you can just replace the second node with a simple register copy. So you can do that even though there are intervening instructions. If you are very well aware of the relation between the location and the intervening code. So suppose that P is not linked to the function f. This P is a pointer and it is very local to this function, and this pointer value has never been linked to the other functions. So that's our supposition. And furthermore, let's assume that we somehow was able to analyze that P and Q are pointing to different locations. In other words, P is not alias with Q. So if that is the case, we are quite sure that the function call to f and the store to Q is never interfering with the value stored in P. And if that is the case, we can just replace y, which is loading from P again, with x, because the value stored in P is never changed. Similar thing happens for store elimination as well. If P is never interfered with the intervening code, then we can remove an earlier store to the same location because no one is accessing and no one is reading from or writing to this location P. And as a result, this write is not visible to elsewhere, and this write is immediately overwritten by the later store to P with the value y. So that's the reason why we can perform such store elimination optimization again with thanks to the alias analysis. So now the question is, how do you deduce that this P and Q are never aliased? If P is allocated and this pointer value is only used as target in the load and stores memory location, pointer location, then you are quite sure that this memory location is never linked to elsewhere. Other functions, other registers can never point to the same location. So that's one example of how to deduce the fact that P is never aliased with Q. Or so we somehow need to track the pointer's lifetime and where the pointers may go with some static analysis. So even if we apply a very simple static analysis, and if we apply a very simple syntactic alias analysis, it will be very helpful in your compiler's optimizations performance. So you can perform such load elimination or store elimination optimizations with alias analysis. So here are a little bit more examples of optimizations, which are store forwarding and loop invariant code motion. Let's discuss first store forwarding. So it is another kind of memory optimizations where a value stored in an earlier instruction may be used in a later instruction as a loaded value. So here, x is stored to the location P, and some function is called, and some location is accessed, and then later it is loaded. So if it is the case, we may be able to say that, oh, this y should be equal to x, because x is stored here, and it is never interfered with other instructions in between the two instructions, and it is loaded again. So this loaded value should be the value stored here, which is x in this case. So y should equal to x, and you can safely replace all the uses of y with x in the remaining of the program. So that is the store forwarding optimization. And again, you can do well on store forwarding with alias analysis, because it allows us to perform optimizations even though there are intervening instructions that may interfere with other memory locations, but that are never interfering with the location pointed to by P. So here is the last kind of such optimization, which is loop invariant code motion. So motion is basically meaning move. We are moving the code. And loop invariant means that we are moving a code out of the loop. So something is an invariant in the loop, so we can just safely move it out of the loop. That is the meaning of this name, loop invariant code motion, moving some code out of a loop. Okay, here is an example. So here in the left side, there's an example. You are writing for each to P, storing a for each to the location pointed to by P, and then calling some function, and then blah blah here. I am storing to some function here. So suppose that this location P is never linked to other functions or other registers. Then we are quite sure that this function F will not interfere with the location P. And Q is never going to be aliased with P in this program, its execution. And as a result, the store to Q is never changing the value of P here. Okay, and we are effectively repeatedly storing the value for each to P without any interference of other codes here. If it is the case, we can safely move this instruction out of the loop. So we can just begin with storing for each to P and then loop here, but without executing the store instruction inside the loop. Why? Because we already stored the value, the same value, before the beginning of the loop. So P is initialized with the same value. And in the left program, P is repeatedly overwritten with the same value without interfering at other locations. And we are just omitting to overwriting to the same value here, same location here. We are just preserving the initialized value here, which is 42. But it coincides with the overwritten value 42 in each iteration of the loop. So it is very safe to just not doing so. We are doing only once before the beginning of the loop, but inside the loop we are not required to write the same value again and again and again. That's the reason why we are able to transform this instruction into no-op, which will be very beneficial if this loop is very tight. Even though this loop is executed multiple times, we are not going to execute only this instruction, which will be very beneficial for the performance of the resulting code. Actually, there are many other optimizations, and you can search for LLVM optimizations to see such other optimizations. There are dead code eliminations, enhanced version. There are some bit level analysis of the dead code elimination even. So even some optimization analyzes which bits of an instruction or the register are actually necessary in the remaining of the code. So for example, if the least significant bit of a register is never used in the remaining of the code, then the optimizer may perform such optimizations that it will ignore the last value of the least significant value of bit of the register value. So such optimizations may be very beneficial when you are doing a lot of bit level manipulations. So the optimizer will automatically reduce the number of instructions and the number of cycles that is necessary for execution, even though you are not very trying hard to do so. And furthermore, there are some enhanced version of GBN, and the most prominent example of this is partial redundancy elimination, which is aggressively trying to optimize removing redundant operations, even though the operation doesn't seem to be redundant. It tries to find a redundancy in the inherent structure of the program and reduce that redundancy. And there are some partial register allocation optimizations. So in our implementation, we only perform register promotion for those locations that are never leaked. But even though some location is partially leaked, we can apply a partial optimization that is helpful to some part of the program. So we may perform such optimizations. And alias analysis, for example, can be enhanced to perform on the entire memory. And there is a analysis named memory SSA, which is basically trying to do a similar thing as SSA for memory locations, etc., etc. So there are really many kinds of optimizations you may want to know. So if you are wanting to know such optimizations, please just Google LLVM optimizations and see the list of optimizations there to see what's going on.